Okay, let's start. So what we did over last 2 weeks was both return ratio and two-port analysis. And I'll show you a table of kind of what happens where in the two ports. So we're going to do that now, and then a look at comparing the return ratio with the two-port a little bit. And you've done that over in the homework as well. So let's say we're going to write the summary for two-port. And this is going to be sort of a table that we're going to classify by feedback type. So with shunt, and then we have shunt series. Then we'll do series shunt, and then series. So the first column is what two-port parameters do we use in analyzing each type of two-port structures, right? So in shunt, we used Y parameters. In shunt series, we use G. In series shunt, H. G and H are hybrids, which kind of mix voltage and current. And so that's because shunt and series shunt feedbacks do mix inputs at outputs, currents at the input, voltage at the output, and vice versa. And then series, both circuits, like the current flows through, so the Z are sort of the natural parameters to use there. Then in terms of the output value, this is kind of what the amplifier is producing. In shunt, a voltage is what the amplifier produces. In shunt series, current. That makes sense because the output type feedback network is series, so that the current is the quantity that sort of flows through the network as being produced by the amplifier. Then series shunt. Anybody guess? Voltage, right? And then series is current, right? Okay. And then we have input values. So if the input type feedback is shunt, what is the input value that feeds into the circuit? Current. And then again, next one is also current. And then in series, we're adding voltage, right? And then here as well. Okay. So transfer function is essentially output value over input value. So here it is VO over IS. So this is trans resistance. Then shunt series is IO over IS. So this is current gain. Next one is VO over VS. So this is voltage gain. And then we have IO over VS, so this is trans impedance, or trans, yeah, transconductance. Okay, so let's look at impedances. These are the ones that we labeled capital I, ZI, for input, and then 0 for output. These are closed loop. So in shunt-shunt, what is the value of the input impedance? Low or high? Yeah, in shunt. Low. What's the value of output? Low. So if you look at the input values, it sort of makes sense, right? At the input, the impedance is low because you want to admit as much current from the previous, which is the input value. And the output is low because you're producing voltage, so you want it to be as ideal a voltage source as possible. Right? Okay, so for shunt series, again, shunt means input is low, but the output is what? High. Again, you look at the output value is current, so obviously you'd want that to be as close to an ideal current source, so it means high. The feedback should help boost the output impedance to high. And then we have high, low, and then high, high. So if you look at this, wherever we have series connection, we essentially have high impedance, right? And wherever we have shunt, then that's low impedance. And now we're going to kind of characterize these types by what it takes to compute the loading for the amplifier, and also to calculate the feedback coefficient. So let's say to calculate loading, so for shunt, to calculate loading at input, what do we do with the output feedback node? Yeah, so we disable the feedback, basically, right? So we short circuit output feedback node. Okay, so in shunt series, what do we do? What do we do with the output in order to calculate the input loading? Yeah. So we open circuit the output. Okay, that's because the feedback quantity is current, right? So we want to kill that, and therefore we open the output. And then look at what's from the input side, what the impedance is. Okay? So again, here in series shunt, we short circuit the output. Same thing as here, because it's the same type of output feedback, right? It's shunt. So whenever it's shunt at the output, we short. And when it's series, we open. So here, in the last case, the output type is series, so we open circuit. Okay, so let's look at the situation when you're calculating the loading at output. So in shunt, what do we do to the input node? Okay, why? I hear open and short. Okay, so let's discuss this. Okay, so you're deactivating the feedback, right? And if it's a feedback circuit that has shunt-shunt connections, you do want to close it to 0, right? The input, because you're still in the forward path, you are applying the voltage to that type of feedback as well, right? So we'll just sketch that real quick. So if I have an input feedback circuit, so this is shunt connection over here, right? If I have a shunt connection on the output side as well, what I was doing for this one, right, I was recognizing that the voltage is the quantity that gets fed back from the output to the input. So what I was doing is I was grounding this node in order to see what's the loading from this side, right? So if I wanted to see how this feedback network affects the output, I do the same thing. I pretend the feedback network is sensing something from the input, right? So in this case, if this feedback was sensing something, it would sense this voltage, right? Because it's connected in parallel with this input. And as it's sensing the voltage and passing it out, the only way I can disable that is by shunting that voltage, right? So in this case, we would short circuit the input node. I know this may be a little bit confusing, but it's sort of a key point, right? So remember that it's all from the standpoint of what the feedback network is sensing and then passing on to the other side, right? So think of the feedback being kind of an ammeter or a voltmeter, right? And if the voltmeter is hooked up in parallel with the line, then it does measure this quantity. If this unit is hooked up in series with everything else, then it's measuring, obviously, the current. Okay, so in this other case, we have, again, shunt at the input. So what are we going to do to that input node? Short it, that's right. Okay, next one. The input circuit is now in this configuration in series, right? So I could say that okay, there is an amp here, and feedback is now in series, right? So there is a current flowing through this. So if I want to see how the feedback is loading the output of the amplifier, right, I want to look at it from this standpoint. What do we do to the input circuit? Yeah, so I disable this quantity. Right? Remember, when we did two-port, what that really means is that this feedback circuit, viewed from this side, had this Y22F, right, which was the conductance, and then it had the controlled source, right? The controlled, so in this case, in the shunt case, it had something that looked like this. Y21F times the current, I in, and then Y22F. So the only way for me to kill this is to basically disable this source. Then I'm really seeing just what this impedance is. right? And the way for me to disable this source is to kill this quantity, I in, with which the input kind of tries to push stuff through the feedback, right? So that's why if the input is serious, we basically open circuit the input feedback node. And then for serious, again, input is serious, so I just open circuit. Okay. I'll erase this, although I don't like doing that, but I just want you to have everything in one spot. Okay. The last thing is how we calculate F. Right. So these two columns over here were helping you how to calculate A, right? And also how to calculate Z in and Z out, right? But now to calculate F, you have to isolate the feedback network itself, right? And then calculate what is the quantity. We usually, when we isolate the network, we will then go and just calculate the quantity from the output to the input. We sort of pretend that the network is unilateral. We can always calculate the other reverse direction too, and then just make sure that the unilateral conditions are satisfied so that we can do those approximations. And we'll touch a little bit on that sort of in the rest of the class. But for this, if we have shunt, what do we do to calculate the F factor? Which quantity are we sensing from the output in shunt? Voltage. So which quantity should we apply to that isolated feedback network in shunt configuration? Voltage, that's right. So apply voltage. At output. And then what do we do? What do we do with the input? Which quantity are we passing to the input in shunt? Current, right? So if that two-port feedback consists of a current-controlled source and some parallel impedance, how do you extract the value of just that current source? Again, what I have is I have this, right? Y11F. And then here I have Y12F times V out, right? So I really am interested in this quantity over here because that is F, right? So how do I, by applying voltage to the other side, right? I know what VO is. But how do I measure, what quantity do I need to measure at this port? And under what conditions to be able to extract this piece? This is current source. So if you measure voltage, you would need to know this quantity as well, right? And then divide. So what do you do to measure it more immediately, easily? Current, but under what conditions? How do you, what do you do to the output in order to be able to force all the current through it? You short it, right? That's great. So you short these two ports, and then what happens? You measure this current, right? Yep.
You short the input, and then you put a test voltage at the output.
That's right. So the total circuit in that configuration would be F You apply the voltage here. Sorry. Let's call this V out, right? And then here, you short, and then you measure the current, right? And this current should be Y12F times V out, or F times V out, right? And this quantity is F. Okay? So apply voltage at output and short circuit input feedback ports. Okay. And measure current. Okay. Oh, we should have had 2 pages for this. We did draw this in the last lecture for at least one type of feedback in terms of blocks, how you do it. So, and then F is I in over VO, right? Okay, so for shunt series, what do? How do we measure F? Which quantity are we feeding back from the output? Maybe I'll do a little cartoon like this. This is F. Which quantity do we get from the output in series, if output is series? Current. So we're going to test with current here. I'm going to put I out. And then what do we do with this other side? It's a shunt side. So what do we do to get, what quantity are we feeding back? So we picked the current, and then in the shunt, remember there is this, something comes in and something feeds back to this node. So what's coming back? Current or voltage? Current, right? Because this Kirchhoff's law does the summation for you, right, at this node. Okay, so same as this case above, at the input, we're looking for current in order to extract this Y12F, right? So what do we do with that input? We short it. Okay, so in this case, we apply current at output and short circuit the input feedback port and measure current. In this case, F is I in over I out. Getting a little bit ugly, but hopefully we'll survive. Okay, next one. I'll draw a box and you tell me what's what. So this is F. We're doing series shunt. So what quantity do we feed back from the output? Voltage. It's shunt. So we're measuring voltage. So okay, I'll draw it as we're applying it. We're applying voltage. And then the input is now in series. So which quantity does the feedback produce to the input? Voltage, right? Because it's a series loop. So applying voltage to the input from the feedback will now KVL add with the source, right? And that will be our feedback equation. That V error is V in minus V feedback. Okay, so to measure that controlled voltage source, right, inside the feedback that produces this V feedback, how do we do that? Okay, so we keep the circuit open, right, and then we measure essentially V in. Right, so F will be V in over VO. Okay, and in this case, we apply voltage at output and open circuit input feedback port and measure voltage. Okay, the last one. We have F. It's series. So what quantity are we feeding back? Current. So here we're going to drive the feedback with I/O. And then, since it's series at the input, which quantity does the feedback produce to the input, right? Voltage. And how do we measure that voltage? With open, right? Our F will be V in over I/O. So we'll apply current at output and open circuit input feedback port and measure voltage. Okay, that's it, piece of cake. So, I mean, you can use this as a cheat sheet if you want, or you can practice a bit and it gets into your habit. I think the key here is to recognize which quantities you're feeding back. So which quantity you're sensing at the output and which quantity you're producing at the output of that feedback circuit to interfere with your input signal, right? And then it will be kind of obvious what you need to do to extract these parameters. As you've seen in two-port, and yeah?
Is it safe to say that the quantity should always be the reciprocal?
Quantity, can you repeat the question?
So if you have like transfer function is V O over I,
Mm-hmm.
feedback factor should just be the reciprocal, that I of current over voltage. Is it safe to generalize that?
Feedback factor. Yeah, I mean, you can assume that because, yeah, that's right. So that still doesn't tell you how to do it, though, right? So you still have to kind of look at the types of feedback at the output and input and figure it out. I think a more involved thing than this table is actually when you do the real circuits, as we said, you would have to go in and always in two-port map, locate where the feedback is and figure out how to turn inputs and outputs on and off and how to map it to two-port and do it. Okay. Let me give you a little bit of a comparison. So we're kind of done, but I'm just going to give you a few tidbits with feedback, but I'm just going to give you a few tidbits in terms of when and how to compare return ratio with AF. We're going to do it on some familiar examples, so hopefully it brings some intuition. So this is return ratio, and we called this loop gain, and labeled it T in some cases, right? So let's do this example. We'll do it numerically so that people kind of have at least one reference point. Okay. So this is our system. We're going to do that GM equals 38.4 millisiemens, and R pi is 5.2 kilo ohms. Those are just values given from biasing. Right? We're going to use them later. And okay, we're also going to use that R naught is 100K. Okay, so just a reminder for everybody, in terms of the return ratio, we would just write it as R pi. We have RF, and then we'll have V test. Just like this. And then I'll just pull RC and RO out of the transistor. So we can say from here that return ratio is, so this will be VR. And then we're opening this because the input is current source, right? So that's a simple schematic for return ratio. And then we'll do GM times R pi. So it's GM from this source times VT times R pi, and then the current divider between RCRO and everything else. R pi plus RF plus RC in parallel with RO. We already did this, so I'm kind of rushing through it. So I can rewrite this, and you'll see why later, as GM over RF, and then here R pi in parallel with RF, and then RO in parallel with RC in parallel with R pi plus RF. Yep. That's a great point. So by definition, return ratio is minus VR over VT. Right. So if I did VR over VT, then that would be negative because I have a pi phase shift here, right? But because of this minus sign, it's actually positive. Okay, so return ratio from here, if we just plug in the numbers, would be 119. You just keep that number. Okay, if we do 2-port, let's see how that would look like. We have I in, and then we'll have R pi. I'm going to label this as VI. And then here we have GMV in. RO in parallel with RC. And then I have here from the feedback, we kind of did this. We had RF, and then the source was also minus 1 over RF times VO. And then over here on the other side, we also had minus 1 over RF times VI and RF. And that now feeds back into this. And this is VO. We managed to kind of get this piece over here by analyzing in the last class kind of what RF feedback looks like. So there's a port 1 and port 2, right, from both sides. Yes?
If you can do it by inspection, can you just skip and write your circuit for A and F? Like, is that common to just not drive the full thing?
Yeah. So as we did it last time, as like in practice, what you would do is kind of this circuit, right? You would just say, okay, I have I in, and then here I have R pi, and then here I have RF, and then what happened with this node, I grounded it because it was shunt, right? It was exactly this table that we talked about. There was voltage being fed back, so I killed that voltage. And then what I'm looking at the output was GMVI, and VI was here. And then what I have here is RO in parallel with RC. And then I have RF. And then again, because it's shunt at the input, right, I treat that as kind of, again, a voltage at the input feeding through the feedback network. So I need to disable that when I'm looking from the output. So that's this. So this is, you ground when shunt, and then here it's also shunt, right? So then this would be your VO here. And you would use this circuit to calculate A. You can do exactly the same thing from the top circuit, right? The way you calculate A is you would obviously disable the feedback, right? And then calculate A. Now, one thing in the circuit below is that there's a slight difference, right? So if I did the unilateral assumption, which is I killed this piece, right? And then I killed the feedback, then what remains is exactly the circuit below, right? But if I don't eliminate the unilateral assumption, then I have a problem, right? So I'm not taking into account this piece over here, minus 1 over RF, which is kind of the feed forward through the feedback loop. Right? And we said that when we did return ratio analysis, it took care of that explicitly through A0. Right? And here I can keep it. If I recognize that it's happening in this 2-port model, I can keep it, and then my 2-port will be accurate, right? But if I go with this, I explicitly don't acknowledge that there is a flow information through the feedback section, right? And I'll make some error. You'll see here what the error is. It's actually not that big. But you can always check, because you can compare this 1 over RF with GM and see whether it's a significant portion, right? Because you see that this minus 1 over RF essentially aligns with GM. So let's write it out so you'll see. Just by looking at the top piece over here, we can write A and F as minus GM minus 1 over RF. This was our Y21A and this was our Y21F, right, in previous analysis. And then we have, here I would divide by Y0 and YI, right? But I can instead just also multiply by the resistances that are seen, right? And so that's kind of easier here. So I'll do R pi in parallel with RF. Those are these two resistors that you see. And then at the output, I have also RF in parallel with RO in parallel with RC. Okay. So this whole thing is my A. And then I'm multiplying by F. In this case, F is minus 1 over RF. Right. So notice that I have to calculate F as minus 1 RF from just analyzing the feedback network, right? And this piece over here. That's how we arrived to this 2-port in the first place. So now, if we want to check the unilateral assumption, we have to figure out what's the relationship of Y21F, which is in this case 1 over RF, right? That's this block over here, and this forward active piece, right? So in our case, this is like 1 millisiemens, right? Because RF is 1K. Sorry, I didn't write it. 1K. Okay. And then GM is actually 38 millisiemens. Okay. So this is indeed much smaller than Y21A, which is equal to GM, which is equal to 38.4 millisiemens. If it's 10, then it's already, if it's 10x difference, it's already much smaller. Nearly 40, definitely small. Okay. So with this, you check. This is unilateral assumption. Okay. With this, you check whether this circuit over here that you would in practice use, much more easily, is kind of what you should be using, rather than some more elaborate representation like this, right? Okay. So when you go and do this, when you calculate A times F, you get 28. Or this is if you do the full analysis. Or you get 29 with unilateral assumption, i.e. neglect minus 1 over RF, Y21F. Right? So if we neglect the flow information simply because that flow is almost 40 times smaller than GM, we're not going to lose much. Okay, we're getting like 1. And AF, we know that our closed loop feedback is kind of is going to be of like A over 1 plus AF, right? Or 1 over F times AF over 1 plus AF. So 28 over 29 or 29 over 30, that's pretty similar, right? Okay, so that's exactly kind of what happens with this. If you do now A closed loop, which is going to be 1 over F AF over 1 plus AF, right? You're going to get like minus 966 ohms or minus 967 ohms in this case over here, right? So 1 ohm difference. That's not a big deal. Okay. If we want to compare it fully with return ratio, A equivalent, and because we did this, I'm just going to sketch it real quick already. We'll have R pi And then we're going to have RF. And we're grounding this because the voltage is, we're just grounding the, nulling the input, which is voltage. And then we have GM VI. This is VI. And then we have RO in parallel with RC. And then here, there is a little bit of a difference. We have RF, R pi, and then we've grounded, nulled the input quantity, which was current, right? So that's why this piece is open. So here, A equivalent takes the loading of the feedback a little bit differently than A. Okay, because in the previous one, when we did A calculation, this was grounded over here. And you see that that actually itself is kind of a big difference between just what. So you see that previously RR was 119 and AF was 28, right? So that's a 28 or 29. That was a big difference. But the difference how we do the termination here will kind of make up for that difference so that our closed loop is kind of the same. So in this case, A equivalent is minus GM times, and then almost identical, RO in parallel with RC. In parallel, now the output is R pi plus RF, and then times R pi in parallel with RF. That's the voltage that develops. For A naught, we have a simpler circuit. R pi, RF, and then this is VO. So AO is R pi over RF plus R pi plus RC in parallel with RO times RC in parallel with RO. And if you redo this, you get something like this. R pi in parallel with RF, and then the same expression. RC in parallel with RO in parallel with R pi plus RF. So then A closed loop will be A equivalent plus AO over 1 plus RR. And if you look at A equivalent, this is actually minus RF times the return ratio. And then this is just a return ratio over GM. So what you get in the end is minus RF plus 1 over GM. And then you get return ratio over 1 plus return ratio. And if you take a look at this, so here, sort of, we only took into account this minus 1 over RF factor, which is the feed forward through the feedback network, when we computed A0, right? So that affected just a normal A equivalent gain by this correction. But it's small, because 1 over GM is much smaller than RF, so really the effect is not that important even here. So here we get minus 974 ohms times 119 over 120, which is minus 966. Okay, the miracle of numbers. Okay, so if you sort of go through the expressions, really the difference between return ratio and AF was in this type of factor, R pi plus RF, but that was sort of made up or compensated for when we include that into the A equivalent loading. So that's why in the end of the day, both are kind of the same values in the end. Yeah?
What about the impedances? Because you multiply or divide by 1 plus RR or 1 plus T.
Sure.
Different.
Yeah, so if you look at the impedances, you will again compute them from what happens to the output node, right? So
Termination takes up for that as well.
yeah. That's exactly kind of the factor. RF plus R pi, or RF in the other case, but here's a bigger divider than in the previous case, right? So in one case, you're dividing by 120, and in the other case, only by 29. But when you're dividing by 120, you're dividing a bigger impedance, which is RF plus R pi, right? So it comes to be the same thing in the end. OK. I don't have much time. We're almost done. But I wanted to sort of just give you a case, and then brave souls can kind of go and play a little bit more about this. But there is a theorem that says when is return ratio equal to A times F. Okay. And everything can be derived on Y parameters, and then, as we've seen in previous examples, all the formulas are exactly the same. You just substitute H, G, and Z parameters, essentially, because there's dualities in these networks. Right? Hopefully, by now, you notice that all formulas looked exactly the same. It's just how we rearrange things. So this condition is true, RR equals AF. When the two assumptions are met. One, we already know that the amplifier feed-forward gain is greater than the feedback feed-forward gain. Right? So signal goes through the amplifier much more strongly than through the feedback network from input to output. But this case was also the case in the previous example that I've shown you, and yet RR was not equal to AF. Right? It was 120 versus 28. So there is another condition that that needs to be met. And this one says that we'll write it as Y11A plus Y11F times Y22A plus Y22F is much greater than Y12A plus Y12F times Y21F. See here, read G, H, and Z, and we're also assuming that YS and YL are lumped into Y11A, Y22A. Right? In other words, the loads are absorbed into the amplifier admittances. Right? The way that this comes around is that if you go and draw this two-port network, same way as we did before, you can calculate explicitly the return ratio for that network. Even though it's represented as a two-port, you can just break the source, Y21A. So if you take the Y21A VI, and you measure this as the return current, and then you apply I test, Y22A, right? And the rest of the circuitry is the same, right, as in the two-port representation. But by going through this loop, you can actually calculate the RR, return ratio of this source, Y21A. Right? And when you do that,